All right. So welcome to this eighth workshop on type-driven development called pronounced TyDe'. And so to illustrate this, I took a picture of my daughter's bedroom because it was not tidy. So we're the tidying experts here, and I use it as a kind of trigger, right? So you go by the corridor and you see this picture. It's like a Python program that just needs structure. So that's why I did this. So we have a great menu this year. We have today we'll have 5 full papers. So it's these 12 pages research papers that I think you can already find them on the ACM Digital Library. And then there are also 7 extended abstracts, so up to 3 pages, and they are posted on the workshop webpage, so you can read them straight away. And it covers a very broad range of topics, which we kind of try to, pack them up. It's not really natural, but essentially there is one session this morning which is on types for types, type-driven types. So you will see inference rules for this morning to just kind of warming up. And then there will be a second session which is type-driven designs, when you want to design software and you use types to help you there. And the first session, which is very close to my heart, is what do you do when you want to get types to be there at runtime? So dependent types and other things like this. Okay, so that's the plan for today, and I think it will cut quite nice with a lot of fun reading the papers. So I would like to start with thanking the contributors. Everyone who submitted a paper to TyDe'. It was very nice, a lot of very well-written papers with a lot of pleasure reading them as in the program committee. You can find the list of the program committee members online. Well, all very good discussions. It was very interesting to be there and to try to drive decisions there. And we did something which was to enlist external reviewers. So I should personally thank them for doing the work, because they did not appear on the program committee, but still they did a few reviews. So Emilio Gallego, Soichiro Fuji, Michael Laurent, Loïc Perrault, and Frédéric Pechansky, as well as Louis Chang. They all pitched in, bringing their expert point of view on some papers. So it was quite interesting to get this narrow focus view on some papers. I should also thank the TyDe steering committee, which was wonderful, and the organizer of ICFP, and especially the workshop chairs, Arthur, Yannick. We saw them roam around because they do all the work, so that I don't have to do any work. So and thank you as well. So I'm very happy not to have to do the YouTube shebang and all that. So thank you for doing this. So we are live on YouTube right now. I mean, my voice is live, my face is not, which I guess is pretty good. And so that's thanks to this wonderful organization. Okay, and let's not forget, so I'm just one PC chair. I'm a co-PC chair, so that means I'm a PC chair in the dual category of workshop. And so let's not forget about Yu Kang, who could not be there today for visa issues and travel was a bit complicated, but she was absolutely wonderful. So she's my categorical dual, right? So when I'm administratively lazy, she is administratively very efficient. So that's why there is a workshop today, because she replied to these emails that I thought, oh man. So she has been wonderful. Okay, that's it for the thanks and for the acknowledgements. And now we have to start the day, and we're starting the day with a keynote. That was also hard work to get you there, but we managed. And so we have Jeremy Gibbons today from Oxford University giving us a keynote on generative programming. Who is Jeremy? Everyone knows Jeremy. Jeremy is on Wikipedia, right? So you know who is Jeremy. Perhaps I should still do my homework. So at University of Oxford. Jeremy is a professor of computing, and he leads the algebra programming team. And it's no small thing, right? Algebra programming is really, that's very the jewel of this, right? It's very tidy in the spirit. It's trying to use often the categorical language to kind of structure what the kind of programs we write and try to understand for algorithms, for programs, what's the underlying mathematical structure. And so Jeremy is carrying this work, and in parts as part of, for example, the IFIP Working Group 2.1, which is kind of a group that carries the flame of the squiggles, right? Among many other things, but that's still a place that where this lives and this carry on this work. And also as well in the Working Group 2.11 on program generation. So we know Jeremy for his work on function programming, his patterns in programming. We also know him for these emails we sometimes received from the Journal of Functional Programming, where he was editor-in-chief. He was very kindly asking you, could you review this thing? He was also the guardian of the pearls, the functional pearls, right? So this torch has moved on, right? But you should still submit to JFP, and now it's open access, so you have no excuse, I'm told. And now Jeremy is still editor-in-chief of a programming journal. Again, very tidy, and the open access journal called Compositionality. So all good reasons to keep sending love letters to Jeremy, as I'm doing right now, through papers. All right. So without much ado, please welcome Jeremy.
Thank you, Pierre, for the very kind words. Is the mic on? Yes, do send me love letters. So, with apologies to those who are on YouTube and don't have a view, I'm wearing this T-shirt, which is a souvenir from ICFP in 2017, which is just helpers, and it's got a little monadic program on the back for what student helpers do. And I didn't think this through, so I was having a chat outside with a colleague, and some poor lost student came up to me and said, "Where do I go?" Yeah, so maybe I should have been a bit more circumspect. I'm going to talk about joint work with my co-authors are credited at the end, Tom Shrivers, Nick Wu, and Ashin Kidney. This is a paper we had at the Maths to Program Construction conference last year, which is another very tidy place, and but it's a conference that happens quite rarely. It's sort of every 3 or 4 years. If you spot it, you should submit something to it. And I suppose without further ado, let me get into it. I'm not sure we're going to get the bottoms of all the slides. So I'll skip anything missing. It's about applicative functors, which I'm guessing you're all familiar with. But they're a bit like monads. They're a way of capturing effectful computation in a pure language. They're a simpler version of monads in the sense that they're less powerful than monads, which means there's more of them than there are monads. So every monad is one of these applicative functors, so states and I/O and all these things. But a few other things are applicative as well. And I'm not going to get into the differences between monads and applicatives, just to say this is about applicatives in the sense that we don't need the extra power that monads provide to tell this story, that we can still exploit it if that extra power happens to be there. And I'm going to construct an applicative functor, and I'm not going to do the extra mile to construct a monad, which will be harder work because it's a stronger property, and I can't, I think, construct the monad for this. So the applicative functors are the sweet spot here. This idea of applicative functors was popularized by Conor McBride and Ross Patterson in a lovely functional Perl. And with some misgivings, I'm going to diverge from their notation. So they're in the Haskell library, they're sort of core Haskell programming style these days, and the Haskell library interface is not the one I'm going to use. This is the Haskell library interface. It's the lower one. I'm going to use the upper one. Connor and Ross were exactly right that the Haskell interface is the one you want for programming with. It's the more convenient interface for programming with. But it's the less convenient one for thinking about the theory of and the implementation of one of these applicative functors, I think. And I'm going to use this different but equivalent interface at the top. In the same way, you may be aware that there's two ways of looking at monad, at least two ways of looking at monads. So there's the Haskell way with return and bind, which is convenient and is the language of do notation, which is on the back of my T-shirt. But completely alien well, not completely alien, but not the natural mathematical construction to category theorists. There's the joke about monads are just monoids in the category of endofunctors. Where's the monoid in return and bind? That's not clear at all. But there's the sort of natural categorical presentation makes the monadic structure clear. So if you're familiar with that difference with monads, it's the same kind of thing going on here. Applicative functors, what you need to be able to do is make a neutral computation. So think of this little f as being a type of computations. It's a parameterized type. So f of int is computations that might have some effects and return an int. There's a skip computation that returns void. Unit type returns no effects. And there's a kind of sequential composition. So if you've got a computation that can return A's and another computation that can return B's, then you can run the first one, run the second one, and you get an A and a B as a result. So this is a kind of unit thing, and this is a kind of pairing thing, and you see that you're going to get monoidal kinds of things out of that. And the laws that you have to satisfy to be an applicative functor are monoidal laws for this structure. So the categorical slogan is that they are strong lax-monoidal functors. Is that better? Or you better? Good. So if it's just on one, it might slide round. Let's see how. So, and then a thing that's in Connor and Walter's lovely paper, it's a short paper with all sorts of riches in it, is this idea of applicative traversal of a data structure. So a data structure is here T, it's another parameterized type, so think trees, but with they're polymorphic types. So there's trees of A's, trees of B's, and so on. And if you have an effectful function that you can do for each element, so you can turn A's into B's but have some effects of class F, then you can traverse your entire tree of A's and turn it into a tree of B's, collecting some effects as you go. So you might do some I/O at every element of the tree, or you might use some mutable state for every element of the tree. Again, with some laws, and I did some work on this, and some other people tidied it up and did it better. Maro Yaskeliov, Andrei Ripacek, Ezekiel Rivas have given a better presentation of it, so that's the one you should read. So there are three laws that say this is a well-behaved notion of traversal over a data structure. So basically you have to visit every element precisely once. Not saying anything about what order, so you could visit a list from left to right or from right to left. You could visit a tree in depth first order or in order breadth first, whatever. Those are all well-behaved, but you have to visit everything precisely once. And there's some naturality properties about the effects as well. And again, I'm not going to get into those. They will be used, but I'll just tread lightly over them. So, for example, this is the way to traverse lists. In Haskell, I should have written this with square brackets. Lists are traversable, and this is how you do traverse. if you're trying to visit every with the empty on, so it's basically just skip. So here I'm doing it in the Haskell presentation, so this is like return the empty list without doing any effects, because there are no elements to visit, so you don't use your effectful traversal body at all. And then for a non-empty list, xcons x's, this is where Connor's clever notation works beautifully. This is a kind of funny application, and it's left associating like function application is. So there's parentheses around the left hand the apply. So if you cross off, if you just write the pure word in white, and you write the funny apply in white as a function application, then you'll see this is just cons applied to f of x applied to traverse of x. So it looks like the identity function. So what you do here is you just use the identity function in a slightly different color, and what you get is traversal. That's quite magical, I think. Very hard about what the traversal should be to get at least one traversal. There's one that sort of follows the structure of the data type in the obvious way. Lists are built with a particular bias, and this is going to be traversal with that bias. You can write a traversal with different biases. You have to work a bit harder to do that, but there's one very natural one that sort of falls out of the data type definition. Right. Best play to put it in the collar. You were right all along.
Okay, now we know. Okay.
Right. So here it is again in the less convenient notation, and you'll see why the convenient one is convenient here. So with apologies, I'm going to be showing you the less convenient notation because what I'm showing you is not so much using it, but defining instances of it. But instead of pure and funny apply, we're going to have unit, which is the void returning thing, and this pairing that takes an f of a and an f of b and makes an f of ab's. And so then you need pairs and curries and uncurries and so on. But that's the price we pay for this slightly simpler interface we're going to be defining. Now here's trees. Here's a data type of trees. There are forests. They're mutually recursive. So a tree consists of a label and the forest of children, and the forest is just a list of trees. Trees are defined in terms of forests are defined in terms of trees. We will see a bunch of functions on trees, and they're all going to follow that pattern. The function on trees will be defined in terms of the corresponding function on forests, and the one on forest in terms of the corresponding function on tree. So here's a tree, root label 3, 2 children with labels, root labels 1 and 4, and a picture of that tree. And here's traversal for that tree. I can't remember if I've got the Haskell one on here as well. No, I haven't. So this is the traversal in the less convenient syntax, but you saw how it worked for lists, and presumably you can follow how this is going to work here. But there's a traversal for trees, which is what you're defining by making an instance of the type class, with a local definition of a traversal for forests. And traversal for trees depends on traversal for forests, and traversal for forests depends on traversal for trees. And so it's just going to traverse every element in one of these trees in the obvious way. You'll visit the root node first, and then you'll traverse each of the children in turn. So you'll traverse the entirety of the left child, and then the entirety of the next child, and the entirety of the third child, and so on. That will be a depth-first traversal. And so it's very similar in principle to the list traversal. In fact, a forest is a list of trees. So to traverse a forest, you traverse every tree in that forest one after the other. So it's a traverse with a traverse. But the outermost traverse here is list traverse because it's a forest, and the innermost one is tree traverse because it's traversing a tree. They're written with the same word, but the Haskell type class resolution mechanism will pick the right instance of traverse for the type. That's the type-driven bit. And it's so formulaic that you don't even need to write this. you can derive traversable as an obvious definition that just arises from the algebraic data type definition. So I don't have to think about that at all. That's depth first. What about breadth first? That's a bit more tricky. And this is something I've sort of bashed my head off and on for, well, since my first ICFP. So for 25 years, I've been bashing my head off this. And I'm not going to take you through all those painful head-bashing exercises unless you ask me. But perhaps you can see, perhaps you would sit down and write it this way. You know how to do breadth-first enumeration of things. It's a queue, basically. You make a queue, you put the tree in the queue, you take things off the queue, deal with one element and put all the other things back at the end of the queue. And so you don't get to them until you've dealt with the highest priority things for everything else that was already in the queue. So that does breadth-first enumeration, but it doesn't follow the structure of the tree in any obvious way at all. How do you do something that doesn't just enumerate the elements of the tree, but gives you back a tree of the same shape again with some other stuff done to it? So it does a breadth-first traversal of the tree. So the example I'm going to show you is breadth-first relabeling. In fact, the example I'm not going to show you is breadth-first relabeling, where you've got a stream of new elements, and you go over the tree and apply these, stick these new elements into the tree one by one in breadth-first order, and get back a tree of the same shape as you started, but with new elements. So this isn't going to do that because you just get a list out of it. You've lost the tree structure by sticking things in queues. You can do it, if you try hard enough, by splitting the tree into its shape and contents. So the shape is just a tree of unit values, no payload. The contents is just a list of elements. So if you can enumerate to get the list of elements, then you can get the list of elements in, well, they'll come out in breadth-first order. And then you can do whatever you like to that list of elements as a list. In particular, you can do a left to right traverse over it. And because they came from the tree in breadth-first order, that will be hitting them in breadth-first tree order. So you could go and fiddle with each of the elements one by one, and then you can sort of undo the shape and contents thing to repopulate the tree from its contents. And you can do that, and shape and contents are both nicely structural things, and the undoing of shape and contents is also nicely structural, but it's multi-pass, and that's a bit awkward. Now, there is a very clever circular program to do it, which is due to Geraint-Jones, and that was what I was working on for my that first ICFP paper, where you relabel the tree in breadth-first order, but so suppose you magically had the list of things that you need to use on the first level, the list of things that you need to use on the second level, the list of things that you need to use on the third level, all carefully partitioned, split up from a long list. If you magically had that, then breadth-first relabeling is not difficult because it can be structural now. You've just got this list of lists of the magic ingredients you need, and you just kind of zip it across the tree, and it works out very nicely. The question is, where does the magic come from? And the magic comes from, you can construct that list of lists in the process of doing using the list of lists. And you can think of it, which is the story Geraint tells me of how he came up with it. It was Christmas, and there's a Christmas tree, and you've got a piece of tinsel, and you put it around the tree, and it goes around the back of the tree, and then what's left of the tinsel goes around the next level of the tree. And so what comes out of the other side, unused, of the stuff that you need, is what you need to feed back in the next level down. And you can write a nice, lazy, circular program to do that, and Geraint does, and it's a one-liner, and it's fantastic. But it's lazy and perverse, and it's hard to see what's going on. It's hard to see how you might come up with that if you weren't already decorating a Christmas tree. And it seems to be essentially about laziness. Now, here's another thing of a circular program. This is what's called the rep-min problem, and it's one that was introduced by Richard Byrd in about 1984 as an argument for why you want lazy programming and let recs in your programming language. So the problem here is you've got a tree with integers and you want to replace all the integers in the tree with the smallest integer that's in the tree. So here's a tree with integers, the same one we had before. We're going to replace everything by 1, which happens to be the smallest thing in the tree. Now, of course, it's straightforward to do that. You go over the tree once and you find the smallest thing, and then you go over the tree a second time with just a map and replace all the things with that one thing. But the challenge is to do it in a single pass rather than 2. And Richard, so we had this paper on, well, I can't remember the title of the paper now, something about circular programs in 1984, and he said, well, look, here's a clever way of doing it. Forget about that line for the moment. There's auxiliaries here that are doing all the work, and again, there's an auxiliary for trees and an auxiliary for forests, and the tree one depends on the forest one, and the forest one depends on the tree one. They're mutually recursive, but that's all productive because it's all things depending on the corresponding function on the smaller things. What this does is it takes a tree of ints and some arbitrary thing of type A and gives you back the minimum int and a new tree where all the elements have been replaced by that one thing of type A. Perfectly straightforward. And this is the perfectly straightforward program for doing it. There's no circular programming or anything here. It's what you'd get by splitting this in 2. So this is, given a tree of ints, you can work out the minimum, that's easy. Given a tree of ints and an A, you can make a tree of A's, that's easy. And they both follow the same recursion pattern over the trees, so you can tuple them together. That's called the banana split theorem in the squiggle tradition. So that's all easy, that's all straightforward. And the clever thing is, well, where does this A come from that you're going to replace everything in the tree with? It's the output from the minimum part. And so that's what happens up here. We're going to call this args function on our tree with some m. What's m? Well, it's the result of doing the recursive call. Well, not the recursive call, it's the result of doing the call. So this let needs to be a let rec. And it only works because the m that comes out is not dependent on the m, sorry, the other way around. The m that comes out is not dependent on the m that went in. If I put in undefined as the m that goes in, I'll still get a proper m coming out, and that's where the productivity of the cyclic program comes from. So Richard talked about this, I presume, at the working group 2.1 meetings that he was going to, that I wasn't because it was before my time. And another member of 2.1, Alberto Peterossi, said, well, that's very interesting, but much more complicated than it needs to be. Here's another way of doing it. And Alberto's program, written in Pascal, which didn't exist when Alberto wrote it, so I'm retrospective consistency kind of thing. The difference is this auxiliary function takes a tree of ints and gives you back a pair with the int, which is the minimum as before, and a function, the function that is the dependency on the thing to be replaced to the tree of replacements. And it's this dependency that Alberto said, that's all you need. You don't need let recs. You just need higher order stuff. It's just a functional program. And now it's just an ordinary eager functional program. And the difference up here is you run awks on a tree and you get a pair with a function u and a minimum m. And then you just apply u to m. So you uncurry apply on that pair. And that's not circular. You call awks on T, you get a pair um. Neither of those is used in the call, so an ordinary let works. And those two stories, breadth first traversal of trees and this rep-min thing, are related, and that's the point of my talk. So perhaps you can guess, perhaps you can write it in your head if you're familiar with the traverse. Each of these is, well, so let's say each component of this, one to compute the minimum and the next one to do the replacing, each of those is independently a traversal over the tree. So you can compute the minimum by just traversing the tree in any order, in fact, because min is commutative, and you get the minimum element. And you can also, independently of that, traverse the tree to replace something. That's just a map, so that's a traverse too. And what's going on here is those two traversals are being fused into one. So rather than two recursive calls, or two calls, one to do min and one to do replace, there's one call, and this is the sense in which Richards is solving his problem about doing it in one, with one traversal of the tree rather than two. Now, don't ask me to justify why that's any more efficient. It's not, in fact. The faster way of doing it is to do it with two traversals. So it's a kind of coding trick. And this is a very artificial problem, but it's an artificial problem that's an abstraction of a real problem in compiler writing, where you want to do a traversal over the AST to figure out all the declarations, and then using that information find out all the uses and link them up to their declarations, which might be forwards and backwards references. So it's about fusing together two traversals into one traversal. So how does that work? So if I've got a single structure, T, a tree, and two traversals that I'd like to do it on it, F and G are the traversal bodies, so F turns my A's into B's with some effects, and G turns my A's into C's with some more effects of the same kind. Can I do that with not two traversals but one traversal? Can I go over my tree and turn all the A's into B's and C's in one traversal, because I'm doing the same order of traversal for both of them? And that will give me a tree of BC pairs with effects from F. And then I want to unzip those two trees to get the tree of B's and the tree of C's that is what's supposed to happen over here. But because I compute both of them in the same order, can I do it with just one traversal rather than two? And the answer is obviously no, in general, because they'll give you different interleavings of effects. These are effectful traversals over trees. So this one, if the class of effects is I/O, then this will do a whole bunch of B kinds of I/O, so the kinds of I/O from this part of the computation, and then all the other kinds of I/O. So it'll do some I/O in French, and then some other I/O in German, and all the French stuff will precede all the German stuff. Whereas this one will do a bit of French and a bit of German and a bit of French and a bit of German. So obviously those are going to be different, so that's not going to work. If it were not I/O, but something that were commutative, a commutative class of effects, then that wouldn't matter. So if you were doing probabilities or something like that, or just reading from some context, the interleaving is not observable, and those two, it looks more plausible that they might be the same, but that's very restrictive, and it doesn't allow us to do all the non-commutative effects, for example, tree relabeling and things like that. So here's an intermediate point. The interleaving is also irrelevant, so there's hope for this equation. If even when big F here, the class of effects, and I apologize for my naming conventions, the class of effects is non-commutative, like I/O, but the things that F does and the things that G does in that class of effects do happen to commute with each other. And what that means is, if I do F on X and get a result, and G on Y, and then G on Y and get a result, that's the same as doing G on Y and getting the result, and then F on X and getting the result. My results were the wrong way around here, so I twist. That's the swap action on pairs. here you get f of x and g of x, here you get g of x and f of x, and what you want is for those to be the same. So that's the statement of the condition f of x commute with g of x. And there's a theorem, which is in our paper, that says if f of x commute with g of x, then these two traversals fuse. So when does that happen? Well, one place where it happens, and what the talk is about, is if the class of computations is a two-phase class of computations, so a class of two-phase computations, let me say. Do some things now, do some things later. And what f says is do things now, and what g says is do things later. Which is to say, if I tell you to do x now and do y later, that's the same as telling you to do y later and do x now. My two instructions have commuted, and then the overall behavior when you follow out your list of your to-do list is going to be the same. So this two-phase computation is the trick to getting this traversal to work, this traversal fusion to work. How can we implement that? Well, it turns out that what you want is something that captures two computations, and deconvolution is the thing. What is deconvolution? Well, I have no intuition for where this comes from in category theory, but this is something that a certain person called Day wrote about, it has some connections with convolution that perhaps you can see if you stare at that hard enough. It's a funny Haskell data type. There's just one constructor. These f and the g are classes of effects. So like monads or applicative functors. So a program that has some effects in one class f and some other effects in another class g, different classes in general, and produces some results of type C, can be obtained in the following way. A program that does f things and returns a result of type A, another program that does G things and returns results of type B, and a post-processor that turns AB pairs into C. So this post-processing thing is sometimes called a co-Unada trick. It's a way to turn this into a functor when it isn't obviously a functor. It now delivers things of type C, and if you know how to turn C's into D's, then there's an obvious way to make it return things of type D. You just post-compose the function, the wrapper. It doesn't matter what you do with the internal stuff. Now, it turns out that if f is an applicative functor and g is an applicative functor, then dfg is an applicative functor. Actually, that's very deep. I told you the joke about monads being monoids in the category of endofunctors. There isn't just one category of endofunctors. There's categories of endofunctors with different monoidal categories of endofunctors with different monoidal structures. And if you use composition, then the monoids are monads. But if you use this, deconvolution as your binary operator, de is a binary operator on applicative functors, then the monoids are the applicative functors. Applicative functors are also just monoids in the monoidal category of endofunctors, just a different monoidal category of endofunctors. So that's cute, not helpful perhaps if you haven't seen it before. So that is Mara Yaskeliov again and Ezekiel Rivas, I think, made that observation. Very nice work again. So deconvolution is the thing. And so here, and deconvolutions, you can think of them as being two-phase computations. One of these deconvolution thingies has within it a computation with classes with effects of class F, and some more computation with effects of class G. I'm going to think of those as the two phases. And so, in particular, if I've got only a computation with effects of class F, I can treat it as one of these two-phase things that just skips the second phase, the G phase. And conversely, if I've got something that only is G's, then I can make it one of these that just skips in the F phase. Now, unit here is the thing from applicative functors. It's the one that returns void and has no effects. That's the skip. And again, apologies perhaps for naming convention, unit L and unit R are just the pure things that explain how pairs are monoidal. So unit R is the right unit of pairing with the unit type. But the nifty thing about this is that the computations in different phases commute. It's just the do X now, do Y later. If I tell you to put X's in phase 1 and then Y's in phase 2, that's the same as telling you to put Y's in phase 2 and X's in phase 1, but the plain data results you'll get out will be in the wrong order. You just twist the data around. Moreover, if your two classes of effects, F and G, are in fact the same, you can run one of these day computations. You run the first phase, and then you run the second phase. And it's just an F computation followed by another F computation, so you just do sequential composition of those two classes of computation. So here's an example. I can say hello world in two phases. I can say, for phase 1 we're going to say hello, phase 2 we're going to say world. Now run those one after the other and it'll say hello world. But I can also say, in phase 2 we're going to say world, and in phase 1 we're going to say hello. Now run them one after the other, we will again get hello world. And you can even mix them up. So you can say in phase 1 we're going to say hell, phase 2 we're going to say world, and phase 1 we're going to say hello, and run them one after the other and you'll get hello world again. These phase 1 and phase 2 are orthogonal to the sequential compositions you do in each phase. So you can sequence a bunch of things together in phase 1. That's not commutative because it's sequencing. You can sequence a bunch of things together in phase 2. That's also not commutative. But the specification of the things you do in phase 1 with the things you do in phase 2 can interleave arbitrarily. So here's how you use that to solve the repmin problem. We're going to, from our tree, we're going to construct a two-phase computation. And I'm not going to show you all the steps about this unless you ask me about it, but let me give you the high-level view. It's a two-phase computation. There are two phases. In the first phase, we're going to go over the tree and collect the minimum value. So in Haskell, the idiomatic way of doing that is using the writer monad. It's a monad, but that means it's also an applicative functor. That's fine. And we're going to write ints, and we're going to use min as the monoidal operation in doing so. So there's a new type wrapper called min that does that for you. So this is a computation that in phase 1 is going to go over and collect the minimum value in the tree. In phase 2, we're going to read from a context, and that will be just picking the value that you computed as it happens in the minimum phase, and that's going to replace every element in the tree with the constant thing from the context. So write as a monad, read as a monad, min gives you a monoid. It tells you which monoidal operation on a carrier type for which there are many monoids you might have chosen. There's a two-phase thing. One phase gathers a whole bunch of information, and then the second phase scatters that information across the data structure. Each phase is an instance of traversal. So you can obviously traverse the tree and collect the minimum by visiting every element once. And you can also obviously traverse the tree and replace every element by a constant by visiting every element exactly once. Moreover, the gathering is going to be phase 1, the scattering is going to be phase 2, so the bodies are in different phases, so they commute, so the two traversals fuse to give you one traversal. So repmin orcs is a single traverse, computing something in this fancy day type. Then, given something in this fancy day type, it doesn't matter now whether it's about mins and monoids and so on, just some type S. You've got something that writes, in phase 1 writes an S and then some phase 2 later reads from that S. you can unpack the day thing. So now X's is a writer computation, Y's is a reader computation, and H is the wrapper, the co-Yonader wrapper for them. Let's undo the representation of writers, and that gives us a value and the written output. Let's undo the representation of readers, and that gives you a function from some context. So let's use S as the thing we pass in as the value of that context, and then we'll get out of that a Y. So we get an XY pair, and the wrapper is exactly the right thing to apply to that to produce a result. But that let has to be a let rec again, because where's this S come from? As input on the right-hand side, it's the output on the left-hand side. But if you do this extraction on that retmin function, then what you get is sort of quite obviously Richard's retmin program. This is the cyclic bit. And this is all the perfectly straightforward, not cyclic, ordinary equational reasoning, squiggly stuff, all very well established. It's only this that is the tricky thing in Richard's paper. And the difference between Richard's paper and Alberto's presentation of it, Alberto's paper, is not to extract these two things in parallel, but to extract them sequentially, one after the other. You extract the first thing, you get a pair XS, you extract the second thing using S, and get a Y, and then post-process X and Y with H. And I don't have them both on the same slides, so you can't see, but well, you can see that this is no longer cyclic. You don't need a let rec anymore. The dependency on this S here on that definition up there is just an ordinary dependency. So a non-recursive let suffices. And Alberto's program is just doing this extraction on the same retmin orgs. But also, perhaps, so it would be helpful to have them both on the same slide. In Haskell, this is the same as that. The dependencies it produces between variables, between declarations and uses, is exactly the same whether you do this two lets in parallel or the one let after another. Only true in Haskell, because this Haskell's let is a let rec. But this is the tweak you need to turn Richard's fancy, clever Haskell only, lazy only program into something that works in an eager language. So that's two-phase computations. You can generalize it to multiple phases. So this is a data type where there's a statically unbounded number of phases. Now it has to be homogeneous. They all have to be in the same class of effects F, because I don't know how to pass in something that will post-process an unboundedly large collection of different classes of effect. But there's something that has only a value, no effectful phases, and there's something that says if I've got an effectful phase and some more effectful phases, then I can make a one longer collection of effectful phases. So think of this as a chain, and this is the end of the chain, and each link of the chain is one more effectful computation, one more phase, and one of these co-Yonader post-processors that puts the results together. So for example, if I have a plain value Z of type A and an effectful computation Y that returns B's with effects in F, and a post-processor K that puts B's and A's together to make C's, then this bit is an effectful computation that returns C's. And then if I have another computation that returns D's and another post-processor that puts D's and C's together to make E's, then the whole thing is a computation that returns E's. And this line here is obviously doing day convolution kind of thing. So what's happening here is, in fact, this is a an iterated Day convolution, a homogeneous iterated Day convolution. So very like lists, which are just homogeneous iterated pairing of things. There's an empty list, and you can pair together a head and a tail to make a longer list. Cons together a head and a tail to get a longer list. Now, this data type, phases, is not new. And in fact, it's the data type that underlies the free applicative functor on a given base functor. So if you've got some arbitrary functor f, not classes of effects necessarily, you can make an applicative using this data type. So this data type is one of the ones that appears in a paper by Capriotti and Capozzi about free applicative functors that was in mathematically structured functional programming some years ago. And this is, so there are various different representations. This is kind of cons free applicatives where the recursive thing is in the right-hand side of the pair, but you could have one where the recursive thing is in the left-hand side of the pair and have SNOC kind of free applicatives as well. And I think there are other ways of doing it too. This is one of the ones in Capriotti and Capozzi's paper, and this is the applicative instance. Now, there's a lot of plumbing going on here, and I'm not going to talk through it. But this plumbing is why I've got this awkward presentation, because the plumbing is even worse in the higher order presentation, the one where these things are functions. At least here it's just pairs that we're dealing with. But what the free applicative does is concatenate. So perhaps you can see here, this is like list append. When you get to the end of the first list, you sort of have all the structure of the second list. And if you're not at the end of the first list, then you strip one thing off x's and you sort of recursively append y's and z's together. So this is assembling computations by chaining them together, sequential composition. And that's what the free applicative does. But that's not what we want here, because I want to say, for the left side of my tree, in phase 1 do this, in phase 2 do that, in phase 3 do something else. The right side of the tree, I want to say, in phase 1 do this, in phase 2 do that, in phase 3 do something else. I don't want to end up with 6 phases. I want to end up with 3 phases. So what I want to do is not concatenation, but zipping. And it's, in fact, what I call a long zip, and what I called a long zip in my ICFP 1998 paper. So nobody else but me likes this, but I think this should be standard stuff. Ordinary Haskell zip takes 2 lists which might be of different lengths, and when one runs out, the result runs out. You get an output that's the shorter, as long as the shorter of the 2 arguments. Long zip gives you an output that is, whose length is the longer of your 2 arguments. What do you do when one runs out? Well, you just copy things from one list, from the other list, input list, to the output. That means long zip has to be homogeneous rather than heterogeneous. It takes a list of length A's of one length, another list of A's of another length, and glues them together into a long list of A's. And where you've got A's in both cases, you need a binary operator to put them together. And where one runs out, you just copy the other one across. And that's what's going on here. So we have some collection of computation in phases, some other collection of computations in phases. They're these chain things, and you put together the first things in each phase, and the first things in each side, and then the second phase things in each side, and the third phase things in each side, sequentially composing 2 things in the same phase. And then when one runs out and the other's still going, well, you just copy that across to the result. And that's what this does, trust me, and don't try and read it. So now, phases is arbitrarily many phases, so you can do the kinds of things you could do with just 2 phases, except there's more of them. So a 2-phase thing, a homogeneous 2-phase thing, is a multi-phase thing. It's just a multi-phase thing with two links in it. So it's a list of length 2. Pairs are lists of length 2. Homogeneous pairs are lists of length 2. And if you've got an int and a effectful computation, you can say do this at phase I. So all you need to know now how to do that, it's inductive on the I. You need to be able to say how to do something at phase 1, that's now, and how to do something later, which postpones it one level down. And then, well, so here's an example of something you can do with more than 2 phases. I had to think a bit about this, but actually this is another one of the examples that's in Richard's paper from 1984 and picked up by Alberto in 1985-6. As Richard said, here's another rep-mini kind of thing. Here's something for which letrec would be nice, and Alberto said, no, you don't need letrec. It can do it just as well this way. So this is a 3-phase computation. The problem is you've got a tree of elements of some ordered type. You want to extract the elements to a list, sort the list, and put the elements back on the tree to get a tree of the same shape, but now with sorted from left to right. And of course, you can do just that. You can go over the tree in one pass with a traversal to collect all the elements. In phase 2, you don't touch the tree, you just do something on this collection of elements. And in phase 3, you go over the list again, go over the tree again, taking things out of the list one by one. Now, I'm doing this. So for phases, it needs to be homogeneous now rather than heterogeneous. So I need to figure out how to do that in a homogeneous class of effects. I'm going to use state. There'll be a list of where I'm storing things and sorting things. And I'm going to push things onto this list and then pop them off the list. You do the same trick. There's a phase 1, a phase 2, a phase 3. They all commute with each other because they're in different phases. So let's put the sorting first, and then the traverse with push and the traverse with pop. And the traverse with push is a whole traverse in phase 1, but that's the same as just an ordinary traverse where the effects stated to be in phase 1. That is to say, phase 1 of a traverse of something is the same as traverse of phase 1 of that something. Phase 1 and traverse commute, and nothing special about 1. Phase I and traverse commute. I can say all in one go, do this traversal at stage 3, or I can say now look at the tree and stick a whole bunch of things in at phase 3. So then we have a modify. In fact, we do have the calculation. No, I don't have the calculation. Ask me later about the calculation. You have a phase 1 with the traverse, a phase 3 with the traverse, so you can make a traverse with a phase 1 and a traverse with a phase 3, and because the bodies are phase 1 and phase 3, they commute, and so those two traversals fuse to make one traversal, and you get this. In phase 2, we're going to modify the stored state, which is a list. I'm going to sort it, and otherwise, we're going to traverse the tree and we're going to push each element in phase 1 and pop a different element in phase 3. And that is manifestly a single traversal over the tree. There's only one traverse in there, which will sort the elements of the tree. So that's just the orgs thing, but you just have to run the phases one after the other. They're all in the state monad so that you can just flatten them all. Now back to breadth first traversal. The same kind of thing applies, except slightly different here. This is 3 phases and always 3 phases. It doesn't matter how big your tree is. Phase 1 we collect things, phase 2 we don't look at the tree, we sort things, phase 3 we put them back. Here I'm going to have a statically unbounded number of phases. There's going to be 1 phase for each level of the tree. So this BFT orcs is the thing that makes the phases, but they're all with the same class of effects, and so I'm just going to flatten them, do them one after the other in the end. And here's what it does. It's just traversal, except these root elements you do now and all the children you do later. and that looks very like the depth first one. In fact, let me show you. I've got the same thing in the Haskell presentation. So let me abandon my categorical presentation of effectful things now. Back to Connor's notation. This is the ordinary depth first traversal of trees that we saw at the beginning of the talk. Visit the root. Visit each of the children. Here I'm calling it DFT, but it's the instance of traverse we had for trees. And you put them together with node. So there's a pure and funny applies. And if you just stick now here and later there, then you get breadth first traversal. And I think that's quite remarkable. I'm delighted at how quickly and easily, how simple that program is, how tidy that program is. And then the fancy breadth first relabeling is you just need breadth first traversal. Once you can do breadth first traversal, then breadth first relabeling is easy. You feed in, let's say, a stream and an infinite list of new labels, just so we don't have to worry about it running out. And at each element, you just pop something off the stream. And the breadth first labeling calls breadth first traversal, and it's the breadth first traversal that deals with the breadth firstiness. That's what it's supposed to do. So all you have to deal with is the pop here. So Geraint's beautiful circular lazy functional program is redundant now because we've got this phases thing. I should say I was delighted to come up with this, with my co-authors, to come up with this fancy breadth first program, which is really tidy and really nice and elegant. Then I discovered that wasn't the first person to do that. So there's a guy called Craig Easterly, who's written I don't know who he is, written a Haskell library of tree traversals, and this is in there. So it's prior work, nothing new under the sun. But it doesn't, I can't claim to be the originator of it, but it's still just as pretty as it was when Craig came up with it rather than me. And I'm going to stop there. I've had my hour. Deconvolution is something worth knowing about, even though it's a bit head-scratchy. But it's the natural monoidal structure that sits underneath applicative functors. And it is what you need for multi-phase computation. So two-phase computations are just deconvolution. And multi-phase computation is just iterating that binary operator. It's a funny applicative instance. Maybe I didn't emphasize this enough. The free applicative has the premise that all you need is f is a functor, and then you can make something that's an applicative functor, and you get the free construction, just like free monads give you a monad structure on something that was not monadic to start with. Let me go back. That's the free applicative, Kaposi and Capriotti. This one, R1, the one that zips, requires you to be able to pair together things at the same level. And so that requires f itself already to be applicative. So if it's applicative horizontally, if you like, here's how to make it applicative vertically. So the types are different, as well as the definitions being different. Richard had this thing about lazy circular functional programs, and Alberto, much less well known in our community because he's really a logic programming guy, said here's how to do it just with higher order features. I didn't know that when I started this work a year or two ago, despite being a member of 2.1 and knowing Alberto very well. It just completely missed me. I think Alberto's papers are very worth reading. Olivier Domvie has written a little bit about this and comparing these two, so I should have known it if only through Olivier Domvie's work. But I really like the fact that the difference between Richard's and Alberto's RepMin programs is just a matter of staging and how you flatten that staging at the end. And I really also like this breadth first traversal, Craig Easterly's invention. Now I have some other thoughts which are sort of still mulling around in my head about software architecture and choreography. these multi-phase computations are a collection of phases indexed by natural number, the level. But there's nothing really that requires it to be numbers, and we're not doing any arithmetic on the numbers. So I have a conjecture about richer structures of indexing. So choreography is a kind of multi-site, multi-location computation, and this is just some computations indexed by their location. So if you want to see if I can make some sense of that, come along to a new workshop on functional software architecture on Friday, where I'm also giving a talk about this. It's a shorter talk, and I'll skip over the tidy-ish details and try and say something interesting about choreography and things. So my colleagues, the paper, it's on my webpage, and this the traversal stuff is stuff I did with Richard. The Repmin stuff is stuff that I inherited from Richard. It was before my time, but influential on me. This paper is dedicated to Richard's memory. Thank you.
Thank you, Jeremy. Any question? You can, if you're online, you can ask them on Discord, and I will replay them back.
Alan Jeffrey, I'm from Roblox. That was very nice. There was a lot of text on those slides. I'm wondering, can I get some pretty pictures out of this? Is there a connection over to string diagrams?
That's an excellent question. I have no idea. There's a lot of categorical structure in here, so you would absolutely hope so. But I don't know, you're the expert. Is there a string diagram story?
I could make a guess.
Yes.
Just wondering if you'd already
No, I haven't already
done the grunt work.
No. Brent.
Hey Jeremy, thanks. That was a lot of fun. Have you thought about? I wonder if you could get multi-phase computations with heterogeneous effects by sort of indexing by a type-level list of applicative functors. Do you think that would work?
So you can certainly do that, and in fact, it's something I've written about. So I was written about in the abstract for FunArch because one of the reviewers asked about it there. So you can, but then you need some indexed way of running it. So how do you, if I've got an F effect and a G effect and an H effect and a K effect and so on, how do I extract them and do them one after the other? Well, you could construct that too. But the nice thing about applicative functors is that they compose in exactly the way that monads don't. So if I've got an F effect here and a G effect there, then I can make one combined class of effects in which both of these appear. In fact, it's just the Day convolution. So what I'm doing, if you like, is already embedding in the homogenizer that would take your heterogeneous ideas and inject them all into some homogeneous supertype.
Hi, Will Creighton from Brown.
Hi.
And thank you for the great talk. Can you go to the slide where you showed the type signature of the Day convolution implementation of Repmin? Yes. Is this type signature constrained enough that if you assume that writer, min, and reader are implemented as you expect, the only valid implementation of this type is sort of performs Repmin? Because, this wasn't true, I think, of the later type signatures where you use the phases type class.
It's not true here either, because of this being fixed int. Nothing stops me, the reader, taking the int and squaring it, or using a different int.
Right.
But here, the S type is now polymorphic, so you can't depend on anything about the S type.
Right.
So maybe if I gave it this polymorphic type, then the implementation I've got is the only implementation.
Right. I just thought it was interesting how much of the computational structure becomes reflected in the type
Yes,
signature,
yes.
and how much it constrains it. Right?
Yes, that's a very tidy question.
Mm-hmm.
Haven't thought about it, but certainly you would need the polymorphic one.
Right.
But I don't know if that's enough.
Oh, it's an interesting connection. Thank you.
Yeah, hi, I'm Peter Diemann from Freiburg. I also had the question about the heterogeneous phases, but that was already gone. But I was wondering, so as far as I remember, Olivier d'Anville had the problem to show that the two traversals are equal. I mean, that the circular program is equivalent to the one where things are sequentialized. So as far as I understand what you're saying, so this is solved by this approach, isn't it?
Yes, yes. I think this is much nicer than Olivier's stuff because there's the sort of categorical structure, the algebraic structure, that is not Olivier's bag. So he's just done it with flattened equational reasoning with functional programs. So he has shown that, I guess, that they're the same, but the argument for that is much more low level than this one.
Yeah, excellent. Thank you.
Hi, hi, Neil Krishnaswamy from Cambridge. So, if you asked me, so I really enjoyed this talk. So, if you asked me, how do you do breadth first traversal?
Yep.
My answer would be, you put it in, you get the adjacency graph of the tree, and then you do some matrix multiplications.
Okay. That wouldn't have been my first guess.
And I was just wondering if you knew, is there like some connection between like sort of this kind of this style of graph algorithms through
linear algebra.
Yeah.
I don't know. I mean, there's a book on graph algorithms via linear algebra or something like that, which looks very interesting and is on my reading list. But it's input, not output, so far. Yeah, I don't know. And it would be nice to use this, in fact, for graph algorithms, because just before Richard died, he and I were working on this book on algorithm design with Haskell. There's whole chapters on breadth first and depth first traversals of graphs, which are all done using queues and stacks, as you might expect, the traditional way. There's a job to be done, a paper to be written perhaps, about maybe you could do it this other way. Richard would not have wanted that, and the book is resolutely simple, which is one of Richard's strengths, but so there's no monads in the book, there's no type classes in the book apart from ord and things like that, no new type classes. It's all how little do we need to get away with telling the functional programming story. So it's absolutely not an exploration of fancy Haskell features. But if you wanted to do an exploration of fancy Haskell features for algorithms, particularly graph algorithms, then yeah, nice idea, thank you.
Any other questions? Oh, yeah. You saw what I did here. I did a breadth first.
Yes.
Yeah, thanks. Yeah, Jennifer Pagan.
Hi, Jen.
So the goal that you were getting to was a single traversal of the tree, the list, the traversal. But it struck me when you were like in the example when you were calling run reader and run writer, and however for multi-phase computations, are those doing those computations? Are you sort of effectively doing a structural traversal again in that later stage, or am I think I'm missing something, but I don't.
No, I think you're exactly seeing why people are always suspicious of Repmin as a convincing example. It's not very convincing. So Richard's cyclic program, I think it's harder to see what's going on. Alberto's higher order program makes it very clear. In one pass, you compute the minimum and a function that, given a new value, will give you back a tree. So that function embeds within it a whole tree structure, and if you give it a value, somehow it's going to have to make a whole tree out of it. So you haven't saved anything, you just moved that bump under the carpet into a different place. So I'm not offering this as an efficiency proving transformation or anything like that, and I don't think even Richard did that in 1984. It said, his argument was, this is a natural way of expressing the problem, and so we should have letrec in our language to allow us to do this. Now, you could argue with that claim even. But I do think So that's my software architecture story. Sometimes the neatest way of expressing the computation you want to do is completely orthogonal to the way you want to end up actually executing it. So I'd like to be able to say here, there's some stuff for phase 1 and some stuff for phase 3, and there's some stuff for phase 2 and phase 4. And you see this in literate programming as well, where, I mean, Ruth's idea for writing programs, Tech and Co were written in Pascal to start with, and Pascal had very strict constraints on the order of the definitions in your program. You had to have all the constants and then all the types and then all the declarations. But in explaining a program, you wanted to say, well, here's a constant and a type and a declaration for this data structure, and here's some more constants, types, and declarations for other data structures. So you'd like to be able to specify that in the sort of natural logical reader order, and something else rearranges them for the Pascal compiler. And similarly, that's what choreographic languages do. You write one unified program for the whole choreography, which then gets endpoint projection is the thing that factors it off into, well, you go and do this bit and you go and do that bit. And if you all talk to each other as we've discussed, then the book will be sold, or whatever it is that your choreography was for. So it's not an efficiency thing, it's an expressivity thing. What's the right way of describing your computation, your problem? But great question, thank you.
Any other question? Oh. You're just making me run.
Gabriel Ardan from Enria. Thank you, it was very interesting. I like the connection with tierless programming, but that's just my thing. I was wondering, so one thing you do when you go from Richard's program to the next one is basically you're forced to use higher order.
Yes.
Which is, as you said, pretty bad for efficiency.
Yes.
I was wondering if there is a way to recover that without going to laziness. And my instinct would be algebraic effects, but I wonder if we can do that, because it seems a bit tricky.
Well, that's another interesting question, because there's another little bit of my brain that's going algebraic effects, and yeah, well, I don't know. We should have a chat. I've never thought of it, and I mean that's why I come to ICFP. I give a talk about X, and somebody sticks their hand up and says, "Didn't you write about Y?" And aren't X and Y related? And I go, "Are they? Oh, that's nice." So thank you. Don't know.
Any remaining question? No? So I didn't see any question on Discord, but there is a comment for you, a gentle comment. So I invite you to have a look there. So I think that's it for our first session. Thanks again, Jeremy.
Thank you.